My dear students, welcome back to our channel. In this video, I will be explaining the BCA third semester subject Operating System Concepts as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is Definition of Operating System OS. An operating system OS is a special software that acts as a bridge between the computer hardware and the user or application programs. It manages all the computer resources like CPU, memory, storage, and input-output devices so that different programs can run smoothly without interfering with each other. Think of it like a manager in a busy restaurant. The manager, OS, assigns tasks to chefs, CPU, manages ingredients, memory, and ensures orders, programs, are completed on time without chaos. For example, when you play a video on your phone, the OS makes sure the video app gets the CPU to decode the video, uses memory to store frames, and sends sound to the speaker. You don't need to manage any of these steps manually, the OS handles it all. In short, an OS controls, coordinates, and simplifies the interaction between users and hardware, making computers efficient and easy to use. Next important short question is 2. Define system calls. Definition of system calls. A system call is a way for a program, user application, to ask the operating system, OS, to perform a task that the program cannot do directly. Since programs cannot directly access hardware like disk, memory, or CPU, they use system calls as a bridge. Think of it like asking permission from a security guard. You, the program, want to enter a secure building, hardware resources. You can't go in directly, so you ask the guard, OS, to let you in safely. Example. When you open a file in a program, it uses a system call like open to ask the OS to access the storage. When you print a document, your program calls a system call to send data to the printer. In short, system calls act as a messenger between programs and the computer hardware, allowing programs to use resources safely and efficiently without crashing the system. Next important short question is 3. Define a process. Definition of a process. A process is a program in action. It is a unit of work that the operating system, OS, manages. While a program is just a set of instructions stored on disk, a process is what happens when the program is actually running in the computer's memory. Think of it like this: a recipe program sitting in a cookbook is just instructions. When a chef starts cooking, process, the recipe comes to life and produces a dish. Similarly, a process takes CPU time, memory, and other resources to execute the program. Example. When you open Google Chrome, the OS creates a process for Chrome. Each tab you open may be a separate process, allowing them to run independently. If one tab crashes, others continue working because each process is managed separately. In short, a process is a running instance of a program that the OS manages efficiently. Next important short question is 4. What is a thread? A thread is the smallest unit of a process that can be scheduled and executed by the CPU. A single process can have one or more threads, all of which share the process's resources like memory, but each thread can run independently. Threads allow a program to do multiple tasks at the same time. Think of it like a team working on a project. The project is the process, and each team member is a thread. They share the same resources, like office space and tools, but each member can work on different tasks at the same time, speeding up the project. Example. In a web browser, one thread handles loading a web page, another handles scrolling, and a third handles playing a video. This way, the browser remains fast and responsive because tasks run simultaneously. In short, a thread is a lightweight process that allows multitasking within a single program efficiently. Next important short question is 5. Multicore programming. Multicore programming is a way of writing programs that can run on multiple CPU cores at the same time. Modern computers and smartphones often have multiple cores in a single CPU, which means they can perform several tasks simultaneously. Multicore programming helps programs use all these cores efficiently to run faster and handle more work. Think of it like a kitchen with multiple chefs, CPU cores. If you have only one chef, cooking a big meal takes a long time. If you have 4 chefs, each can cook a part of the meal at the same time, and the meal is ready faster. Example. Video editing software can render multiple frames in parallel. A web server can handle many user requests at the same time using multiple cores. In short, multicore programming is writing programs to work faster by using all CPU cores together, improving performance and efficiency. Next important short question is 6. Mention the thread issues. Thread issues. While threads make programs faster and allow multitasking, they also come with some challenges or issues that programmers must handle carefully. 1. Synchronization problems. When multiple threads try to access the same data at the same time, it can cause errors or inconsistent results. 2. Deadlock. Threads may get stuck waiting for each other forever, stopping the program from progressing. 3. Resource sharing conflicts. Threads share memory and resources. If not managed properly, one thread can overwrite another thread's data, causing crashes. 4. Debugging difficulty. Because threads run simultaneously, finding and fixing bugs is harder than in single-threaded programs. Example. In a banking app, if 2 threads try to update the same account balance at the same time, the final balance may be incorrect if synchronization is not handled. In short, thread issues are mainly about managing shared resources and timing carefully to avoid errors. Next important short question is 7. What is CPU scheduling? CPU scheduling is the way the operating system, OS, decides which process gets to use the CPU next when multiple processes are waiting. Since a CPU can handle only one process at a time, scheduling ensures that all processes run efficiently and the computer stays fast and responsive. Think of it like a ticket counter at a busy train station. Many people, processes, are waiting, but only one person can be served at a time. The staff, CPU scheduler, decides who goes next to avoid long waits and keep things moving smoothly. Example. If you are watching a video, downloading a file, and running a game, CPU scheduling decides how much time each task gets on the CPU. This ensures the video plays smoothly while the download continues in the background. In short, CPU scheduling is the OS's smart way to share the CPU among processes fairly and efficiently. Next important short question is 8. CPU scheduling algorithms. CPU scheduling algorithms are rules that the operating system, OS, uses to decide the order in which processes get the CPU. Different algorithms are used to make sure the CPU is used efficiently, processes don't wait too long, and the system runs smoothly. Some common algorithms. 1. First come, first served. FCFS processes are served in the order they arrive. 2. Shortest job next. SJN SJF, the process with the shortest execution time goes first. 3. Round robin. RR, each process gets a fixed time slice in turns. 4. Priority scheduling. Processes with higher priority are served first. Example. Imagine a printer queue. FCFS prints documents in arrival order. SJF prints small documents first. RR gives each document a few pages, and priority prints urgent documents first. In short, CPU scheduling algorithms are ways the OS decides who uses the CPU and for how long to keep the system efficient and fair. Next, Unit 1. Long questions. First important long question is: 1. Explain about computer system organization. Computer system organization. Computer system organization refers to the way the hardware components of a computer are arranged and connected so that the system can work efficiently and perform tasks correctly. It focuses on the internal structure of the computer, how the CPU, memory, input-output devices, and storage work together, and how data flows between them. Think of a computer like a factory. The CPU, Central Processing Unit, is the manager, responsible for controlling operations, performing calculations, and making decisions. Memory, RAM, is like the worker's desk, a temporary space where data and instructions are kept while tasks are being executed. Storage, hard disk or SSD, is the warehouse, where all long-term data is stored until it is needed. Input devices, keyboard, mouse, scanner, bring in raw materials, data to the factory, while output devices, monitor, printer, speakers, deliver the finished product to users. Buses and connections act like conveyor belts, moving data and instructions between components quickly and efficiently. Example. When you type a document in MS Word. 1. The keyboard sends your input to RAM. 2. The CPU processes the keystrokes, applies formatting, and updates the display. 3. The monitor shows the letters on the screen, output. 4. When you save the file, the data is transferred from RAM to the hard disk for permanent storage. This organization ensures that each component knows its role and works together without conflicts, making the computer fast, reliable, and efficient. In short, computer system organization is the logical and functional arrangement of hardware components that allows a computer to execute programs efficiently. Understanding it helps in learning how computers handle data, perform tasks, and communicate between hardware and software. Next important long question is: 2. Discuss computer system architecture. Computer system architecture. Computer system architecture refers to the design and structure of a computer system, focusing on how the hardware and software components interact and communicate to perform tasks efficiently. While computer system organization deals with how components are arranged, architecture emphasizes how they function, process data, and follow instructions. The main components of computer architecture are: 1. Central Processing Unit, CPU. The brain of the computer that executes instructions and controls all operations. It has two parts. Arithmetic Logic Unit, ALU, performs calculations and logical operations. Control Unit, CU, directs the flow of data between CPU, memory, and input-output devices. 2. Memory. Primary memory, RAM, temporary storage for data and instructions during execution. Secondary memory, hard disk, SSD, permanent storage for data and programs. 3. Input-output devices. Input devices like keyboard, mouse, and scanner provide data to the system. Output devices like monitor, printer, and speakers display or deliver results. 4. Buses. Electrical pathways that transfer data, instructions, and signals between components. Example. When you watch a video on YouTube, the CPU fetches instructions from memory, the ALU decodes and processes video frames, input devices handle commands, like play pause, and output devices display the video on the screen. Data flows via buses to coordinate everything. Key points. Computer architecture defines instruction sets, data formats, addressing modes, and how components interact. A well-designed architecture ensures fast, reliable, and efficient performance, even for complex applications like gaming, video editing, or multitasking. In short, computer system architecture is the blueprint of a computer, showing how hardware components and software instructions work together to process data, execute programs, and produce results. Understanding architecture helps students grasp how computers operate efficiently and make better use of resources. Next important long question is 3. Operating system structure. The operating system, OS, is like the manager of a computer, controlling hardware and software to make the system run efficiently. The structure of an OS refers to how it is organized internally to provide services, manage resources, and execute programs. There are several common structures of operating systems. 1. Monolithic structure. All OS services, like process management, memory management, and device drivers, run in a single large block of code. Example, traditional Unix OS. Advantage, fast execution. Disadvantage, difficult to maintain and debug. 2. Layered structure. OS is divided into layers, each performing specific tasks. Lower layers control hardware, higher layers provide user services. Example, the OS. Advantage, easy to debug and maintain. 3. Microkernel structure. Only essential services, like communication between hardware and processes, are in the kernel. Other services run in user space. Example, Mac OS, Minix. Advantage, more reliable and secure. Disadvantage, slightly slower due to more communication overhead. 4. Modular structure. OS is divided into modules, which can be loaded or removed as needed. Example, modern Windows and Linux kernels. Advantage, flexible and easy to extend. Example in real life. Think of an airport. The runway and air traffic control are like the kernel, handling essential tasks. Check-in counters, baggage services, and lounges are like modules or layers, providing additional services. Passengers, programs, use these services without worrying about the inner working of the airport. Key points. The structure determines how the OS manages processes, memory, files, and devices. Choosing the right structure affects efficiency, reliability, security, and maintainability. In short, the operating system structure is the internal design of the OS, showing how its components work together to manage resources, provide services, and allow multiple programs to run efficiently and safely. Next important long question is 4. Write about operating system services. Operating system services. An operating system, OS, provides various services to make computers easy to use and manage. These services act as a bridge between the user, applications, and hardware, ensuring programs run efficiently and safely. The main operating system services are 1. Program execution. The OS loads programs into memory, executes them, and handles termination. Example, when you open MS Word, the OS loads it into memory and runs it. 2. I/O operations. The OS manages input and output devices like keyboard, mouse, printer, and monitor. Example, typing on a keyboard or printing a document is handled by the OS. 3. File system management. The OS provides organizing, storing, reading, and writing files in storage devices. Example, saving a file in a folder on a hard disk or USB drive. 4. Communication services. The OS allows processes to communicate with each other, either on the same computer or over a network. Example, chat apps use OS services to send and receive messages between processes. 5. Error detection and handling. The OS detects hardware or software errors and takes action to prevent system crashes. Example, if a USB device is removed unexpectedly, the OS shows a warning to prevent data loss. 6. Resource allocation. The OS decides how CPU, memory, and devices are shared among processes. Example, multiple apps running simultaneously on your phone or computer get fair CPU time. 7. Security and protection. The OS protects data, programs, and resources from unauthorized access. Example, password protection, user accounts, and file permissions. Example in real life. Think of the OS as a hotel manager. It allocates rooms, memory, assigns staff, CPU to tasks, handles guest requests, I/O, and ensures safety and security. In short, operating system services are essential functions provided by the OS that make computers efficient, reliable, secure, and user-friendly, allowing multiple programs and users to work together smoothly. Next important long question is: 5. Explain types of system calls. Types of system calls. A system call is a way for a program to request services from the operating system OS. Since programs cannot directly access hardware like memory, CPU, or disks, system calls act as a bridge between the program and the OS. System calls can be grouped into 5 main types. 1. Process control. These calls manage processes, such as creating, terminating, or stopping a process. Example, fork creates a new process in Linux, exit terminates a process. 2. File management. These calls allow programs to create, read, write, open, close, or delete files. Example, open opens a file, read reads data from it, and write saves data. 3. Device management. These calls let programs access hardware devices like printers, keyboards, or disks. Example, IOCTL in Linux configures a device, or read and write access device data. 4. Information maintenance. These calls provide information about the system or process. Example, getPID returns the current process ID, time, returns the system time. 5. Communication. These calls allow processes to communicate with each other, either on the same system or over a network. Example, pipe creates a communication channel between two processes, send and receive, handle messages. Example in real life. Think of system calls like asking a manager for help. If you want a document printed, you ask the manager, OS, not the printer directly. If you want to save a file, the OS handles the storage safely. Key points. System calls make programming simpler and safer, as programmers do not need to manage hardware directly. They provide a standard interface to interact with the OS, ensuring efficient resource use and protection. In short, types of system calls are tools provided by the OS to manage processes, files, devices, communication, and system information, making programs run smoothly and safely. Next important long question is: 6. Process scheduling. Process scheduling is a method used by the operating system, OS, to decide which process should get the CPU next when multiple processes are ready to run. Since a CPU can execute only one process at a time, scheduling ensures that all processes get a fair share of CPU time and the system works efficiently. The OS uses schedulers to manage processes. 1. Long-term scheduler decides which jobs from the job queue are admitted into memory for execution. 2. Medium-term scheduler temporarily pauses or resumes processes to improve performance or handle memory efficiently. 3. Short-term scheduler CPU scheduler chooses which ready process gets the CPU next. This happens frequently. Example in real life. Imagine a busy restaurant kitchen with one chef, CPU, and multiple orders, processes. The chef cannot cook all dishes simultaneously, so the kitchen manager, OS, decides which dish to prepare first, ensuring every customer gets served quickly and fairly. Objectives of process scheduling. 1. Maximize CPU utilization. CPU should not be idle. 2. Reduce waiting time. Processes should not wait too long. 3. Ensure fairness. Each process gets a chance to execute. 4. Improve system throughput. More processes are completed in less time. Example in computer. Running a video, music player, and browser at the same time. The OS schedules CPU time so the video plays smoothly, music continues, and the browser responds to clicks. Key points. Process scheduling is essential in multitasking and multi-user systems. Different CPU scheduling algorithms, like FCFS, SJF, round-robin, priority, are used to implement it efficiently. Proper scheduling ensures fast, fair, and responsive systems. In short, process scheduling is the OS strategy to manage multiple processes, giving each process the right amount of CPU time, keeping the system efficient, fair, and responsive for users. Next important long question is 7. Write about multithreading models in detail with an example. Multithreading models. A thread is the smallest unit of a process that can be scheduled and executed by the CPU. Multithreading allows a process to have multiple threads running concurrently, which improves performance, responsiveness, and resource utilization. There are several multithreading models, mainly based on how user-level threads, ULTs, and kernel-level threads, KLTs, are mapped. 1. Many-to-one model. Multiple user threads are mapped to a single kernel thread. Advantage: simple and easy to implement. Disadvantage: if one thread performs a blocking operation, all threads are blocked. Example: early Linux user-level thread libraries. 2. One-to-one model. Each user thread is mapped to a separate kernel thread. Advantage: if one thread blocks, others can run. Disadvantage: more overhead due to multiple kernel threads. Example: Windows and modern Linux threads. 3. Many-to-many model. Many user threads are mapped to many kernel threads, allowing the OS to manage threads flexibly. Advantage: combines benefits of previous models, efficient and responsive. Example: Solaris OS threads. 4. Two-level model, hybrid. Similar to many-to-many, but some user threads can be bound to specific kernel threads, giving more control over execution. Example: Windows NT supports hybrid threading. Real-life example. Imagine a restaurant with multiple chefs, threads. Many-to-one, all chefs share one stove, kernel thread. If the stove stops, everyone waits. One-to-one, each chef has their own stove. If one stove fails, others continue cooking. Many-to-many, multiple chefs share several stoves efficiently. To level, some chefs have dedicated stoves, while others share. Key points. Multithreading improves responsiveness, CPU utilization, and parallelism. Choosing the right model depends on system resources, performance needs, and complexity. In short, multithreading models define how user threads interact with kernel threads, allowing programs to run multiple tasks efficiently, utilize CPU cores effectively, and remain responsive to users. Next important long question is 8. Write a short note on scheduling criteria. Scheduling criteria. Scheduling criteria are the standards or measures used by the operating system (OS) to evaluate how well a CPU scheduling algorithm performs. Since multiple processes compete for the CPU, the OS needs criteria to choose the best process to run next and ensure the system is efficient, fair, and responsive. The main scheduling criteria are 1. CPU utilization. The goal is to keep the CPU busy as much as possible. Example, in a gaming PC, the CPU should stay active to render frames smoothly. 2. Throughput. The number of processes completed per unit time. Example, a server processing 1000 requests per second has higher throughput than one processing 500. 3. Turnaround time. Total time taken for a process to finish execution after submission. Example, if a student submits an assignment online at 9 a.m. and it's graded by 11 a.m., the turnaround time is 2 hours. 4. Waiting time. Total time a process spends waiting in the ready queue before execution. Example, if your print job waits 5 minutes before the printer starts, that is waiting time. 5. Response time. Time from submission to first response. Important for interactive systems. Example, when you click a link in a browser, the time until the page starts loading is response time. 6. Fairness. Each process should get a reasonable share of CPU without being starved. Example, in a multi-user system, no user's program should dominate CPU time. Real-life analogy. Think of a restaurant kitchen. CPU utilization is equal to keep chefs busy. Turnaround time is equal to time to cook a dish. Waiting time is equal to time a dish waits before cooking. Response time is equal to time until the first bite is served. Fairness is equal to all customers get attention without ignoring anyone. Key points. Scheduling criteria help the OS select the best scheduling algorithm based on system goals. Different systems may prioritize throughput, responsiveness, or fairness depending on the use case. In short, scheduling criteria are performance measures that help the OS schedule processes efficiently, ensuring fast, fair, and smooth system operation.